Good morning, my dear students. So again, in this class, I am going to tell you about the new topic, that is the forced vibration due to excitation of a support instead of the mass. Okay. So in free vibration, what we studied with respect to force, with respect to the mass, we are going to study it. Okay. So in this topic, we are going to derive an equation that is an absolute motion and the relative motion equation. Okay. So I told you in forced vibration means nothing, means what? So the vibration takes place, or in any system the vibration takes place due to the external forces. External periodic force is called as a what? The force vibration. Okay. So what all are we are going to derive in this equation? We are going to neglecting the mass weight, what the formulas are generating with respect to the particular system or body. Okay, that we are going to take, and with the help of a D'Alembert principle we are going to derive. Okay. So here this question is also very important for the point of examination. Okay. So they may ask you direct around 8 to 10 mark question. Okay. Explain the excitation of a support instead of the mass. Okay. Otherwise they may ask you in divided. Okay. They will do here. In this case we are going to get the two concept, that is first one is an absolute motion and relative motion. Okay. They may ask you direct also write a note on absolute motion and relative motion. Okay. So this is also very important under the model fifth vibration, that model fifth in DOM. Okay. So here, so told, so introduction, nothing but even why we are going to study this. Okay. What is the okay. So even if you take the general equation, that is even general concept, even any locomotive vehicles or a normal vehicles, it is moving on a road surfaces. Even the road surfaces may be that up and down, that even or uneven. Okay, whatever that. Okay. If the road is in uneven condition, that is up and down movement takes place, that is the vehicle movement is what? The up and down movement takes place. Okay. If that happens in the road, okay, there will be a relative motion between the vehicle wheel and the road surface. Okay. That we are going to explain in this equation, that is in this concept. Okay. So we are going to derive the equation of the what? Forced vibration and amplitude vibration. Okay. So here, we are going to get the two types of support. Okay. So that what we, there are even the road is the vehicle is moving on a road surfaces, there is a two types of support. One is absolute, another one is a relative motion. Okay. So that we are going to derive this in this class. Okay. So what do you mean by absolute motion? Okay. So here if you derive this equation, we are going to have some general knowledge. Okay. That is what? The here figure A shows the equilibrium position and figure B shows the displacement, displaced position. Okay. So let us consider a spring mass damper system. Okay. At the top this is a mass. Okay. And this is a stiffness, and this is a spring, and the last one is a base or support. This is fixed to the ground level, that is equilibrium position. Okay. Here there is a harmonic wave equation, that is y is equal to y sin omega t. Okay. So where here x dot x double dot stands for what? X is the displacement, and x dot is the velocity, and x double dot is an acceleration. Okay. So even if you differentiate with respect to x, you are going to get the velocity. Again, if you differentiate, you are going to get the double dot, that is x double dot. Okay. So now the figure A shows the equilibrium position of a spring mass damper system. Okay. To avoid the vibration which is present in the ground, which is going to transfer in the machine to the ground level. Okay. So second figure B shows the displaced position. Okay. The spring mass damper system is just to displace at a distance of y in vertical motion. I shown here in the vertical motion. Okay. So the support distance at what? To at a y distance we are going to displace, and the top side, the total mass, again it is displaced at a distance of x minus y. Okay. That x minus y is called as absolute motion. Okay. X and y, that equation what? At a displaced, that we are going to derive in this equation. Okay. So figure A shows the equilibrium position, figure B shows the displacement, that is the displaced position. Okay. The x minus y is the displaced position, that is called as absolute motion. Okay. So here the vibration, that is the motion, takes place in vertical direction, not in horizontal direction. Okay. So here second, so how many forces are acting on that particular element, that is mass. Okay. So here there is a three forces acting on that element. One is a spring damper force, this is a spring damper force, and the damping, there is a spring force, damper force, and here the inertia forces will be acting on that. Okay. Now even if you consider this free body diagram, so in the next slide, so take the mass at the top, the inertia forces which will be acting in opposite direction to the motion, and here the downward two external forces, that is a spring force and damper force. Okay. So k x minus y and c is equal to x dot minus y. This is the free body diagram. Based on this diagram, we are going to derive the equations. Okay. here the x and y are called as an absolute amplitude, and relative amplitude is called as z. Okay, x minus y, the difference is called as z. Okay, z is called as relative amplitude, remember. So this is very important in the while solving problem also. Z stands for relative amplitude, x and y stands for absolute amplitude. Okay, so now one by one we are going to derive now. So first I am going to take the absolute amplitude, that is the absolute motion. Okay, so here let us consider the y is equal to absolute harmonic displacement support. Here I shown y is nothing but what, absolute displacement. Okay, so here in the diagram I shown, so here y is equal to absolute amplitude. Okay, so this is an y is amplitude vibration, that is an amplitude motion. Okay, so that I shown here. So y is equal to what, y sin omega t. So the here it is in a that is a equation. So y is equal to y capital Y sin omega t, we already know this. Okay, so differentiate with respect to this. So y we are going to get y dot, that is not differentiate, just to rearrange this equation, that is differentiate with respect to y, that is sin y sin omega, y is constant omega, w by cos omega will be there. Okay, so I wrote here sin, this is a cos. Okay, so now x is equal to what, absolute displacement of the mass. Okay, remember this, y is absolute harmonic displacement support, and here the support equation what, y is equal to sin omega t, and x is the absolute displacement of mass m. Okay, so now from the free body diagram according to the D'Alembert principle. So D'Alembert principle said that what, the sum of the forces acting on the particular element or machine or a body is equal to 0, that is summation of inertia forces plus external forces is equal to 0. Okay, so here there are three forces are acting on that element. So downward direction you are going to take the you are going to consider the positive sign, and the upward direction you are going to consider the negative sign direction. Okay, so here all are acting downward direction only, so all the forces are acting downward, so consider positive. Okay, according to the D'Alembert principle state that what, the summation of the inertia forces plus external forces is equal to 0. Okay, so here the extra inertia forces is what, mx double dot, and plus c external forces are, there are two forces, spring forces and the damper forces. Okay, that you have mentioned here, c is equal to x dot minus y dot plus k x minus y is equal to 0. Okay, just to multiply this okay, mx double dot as it is, just to multiply this, c x dot minus c y dot plus kx minus ky is equal to 0. Okay, therefore the mx double dot plus c x dot minus c y dot plus kx minus ky you are going to get. But you can the negative sign you just transfer to the that direction. Here negative signs are the minus cy dot and minus ky. Okay, so mx double dot plus cx dot plus kx is equal to what, ky plus cy dot. Okay, so this is an equation what we derived from that. Okay, equation number 1. But we have know that the here the y is there, y dot is there. Okay, but we know the value of y. Okay, y is equal to what, y sin omega t. This is the harmonic wave equation. Okay, again differentiate this y dot is equal to, so differentiation of this is what, sin is cos. Okay, omega is y is constant, omega cos omega t. So it's just to substitute these two equation in this equation number 1, you are going to get this. Okay, so left hand side as it is, that is LHS is as it is, so just to substitute y value and y dot value. Okay, so here in the both the side you are going to get the y is common, so take the y is common, y is equal to k sin omega t plus c omega cos omega t. Okay, so here just to modify this equation again, so you divide and multiplied by RHS only. So square root of k square plus c square omega square, this step is very important, so you just to remember this. Okay, so divide and multiply on the both the side on the RHS, you are nothing losing. Okay, it is same only, just to divide, just to modify this equation from the RHS. Okay, if you multiply that, so what we are going to get, y is equal to square root of k square plus c square omega square. Okay, so k divided by, you are going to divide here, so here multiply and divide here. Okay, k square plus c square omega square sin omega t plus again c omega, so again divide square root of k square plus c square omega square cos omega t. Okay, so once you divide this, so let us assume where cos alpha is equal to k, okay, and sin alpha is equal to this c omega. Okay, so y is equal to again, so square root of k square plus c square y square, so assume cos alpha sin omega t plus sin alpha cos omega t. Okay, where cos alpha is equal to what, k divided by square root of the k square plus c square omega square, and sin alpha is equal to cw, that is angular circular frequency whole divided by square root of k square plus c square. Okay, so now just to modify this equation, this is in the form of sin a plus b formula. Okay, so cos alpha sin omega t plus sin alpha cos omega t is nothing but what, sin a plus b formula, so that you write, just again you modified here, so I wrote here sin omega t plus alpha. Okay, so y is equal to square root of k square plus c square omega square, so into sin of omega t plus alpha. Okay, so see this sin a plus b formula, if you simplify this you are going to get the same. So give equation number 2 for this. Okay, Now we know that from the equation of the force vibration for a constant external excitation, so the already this equation we know that, okay, this is general equation for the harmonic external excitation, okay. Mx double dot plus cx dot plus kx is equal to f naught sin omega t. So this is a normal general derivation, general equation we already studied. So give equation number 3, okay. So now you compare the equation number 2 and 3. So in place of here f naught value, what we have, y square root of k square plus c square omega square, okay. So compare equation, you are going to get f naught is equal to y square root of k square plus c square omega square. Give equation number 4. But if you want the steady state amplitude solution equation, we know that x is equal to xc plus xp, that is x is nothing but what, complementary function and particular function, okay. So where xp is equal to what, capital X of sin omega t plus alpha minus that is alpha minus 5, okay. So this is about the phase angle lagging, it shows the phase angle lagging and leading, okay. So just you remember this equation, this step is very important. Xp is equal to x of sin omega t plus alpha minus 5, okay. So we know that the steady state amplitude x is equal to what, f naught divided by k square root of 1 minus omega by omega n whole square again square plus 2 theta omega by omega n whole square, okay. So this equation you already derived, okay. So this is also steady state amplitude, this also derivation is there, okay. So wherever f naught is there, we know we have the value of f naught. Just to substitute f naught value in this, y is equal to square root of k square plus c square omega square divided by k, okay. So down denominator as it is, okay. So we want the relative amplitude motion, means x and y are called as relative amplitude motion, okay. So in the x by y, this y you can transfer right hand side direction, so you are going to get what, this, okay. So again just to modify this equation, c square omega square by k is equal to what, so just you modified here, okay, c omega by k 2 theta omega by omega n, okay. C omega by k is equal to what, 2 theta omega by omega n, okay. Therefore x by y is equal to what, square root of 1 plus 2 zeta omega by omega n, okay. So just we have some substitute here, okay. So if you substitute, you are going to get this equation. So x by y is square root of 1 plus 2 zeta omega by omega n whole square whole divided by square root of 1 minus omega by omega n whole square to the whole square plus 2 zeta omega by omega n whole square, okay. So this is the equation for what, the relative amplitude equation, okay. So that is what, the amplitude absolute motion, okay. So this equation is called as absolute motion. So up to now we have to derive this equation, okay, where x and y stands for what, this x is amplitude of the body of the machine or the given component, and y is equal to amplitude of the support, okay. The ratio of x and y divided by y is called as displacement transmissibility or a motion transmissibility or the absolute motion. So this is about what the equation derivation for the absolute motion, okay. Along with that, the phase angle. So phase angle have to remember only this, okay. Phi is equal to tan inverse of 2 zeta omega by omega n whole divided by 1 minus omega by omega n whole square, okay. So this is the phase angle you have to remember. From this equation you have to remember this equation, x and y equation, and this phase angle equation, okay. So this is about the lagging and leading equation. Wherever lagging is there, you are going to use this equation, okay. So second case is what, the relative motion. So already I told you relative motion is indication what, z, okay. So that x minus y is equal to z is called as a relative motion in the given problem, okay, that in the given concept, okay. Let us define the relative motion of the mass with respect to support rather than the absolute motion, okay. So here if z is equal to x minus y is the relative motion of the particular mass and to the base, the equation for the motion can be written as mz double dot plus cz dot plus kz is equal to minus my double dot, okay. So give equation number 1. So here you are going to consider the minus sign because the forces acting upward direction, okay. So wherever x is there, just to substitute here z, okay. So mz dot double dot plus cz dot plus kz is equal to minus my dot, okay. Give equation number 1, okay. So this is the diagram indicate the relative motion between the road surfaces and the vehicle, okay. So let us consider this is a component, a machine, okay. So vehicle also having the mass, stiffness, spring, okay. This is a static equilibrium position, let us say a ground, a road, okay. So this is the uneven road surfaces, okay. So this stands for uneven road surface up and down, okay. So this from this side to here complete one cycle. So the here it is a harmonic equation. So harmonic equation means let us use sin omega t, okay. Y is the excitation is y sin omega t, okay. So here the vehicle or any particular component, it is moving in a uneven, that is a wave equation form, okay. So on the road surfaces, okay. within some velocity kilometer per hour, and here the acceleration displacement is x of t. Okay, so this is the block diagram. So here the equation, here the vehicle moving in uneven, that is the harmonic wave form. So let us assume the y is equal to sin omega t. Okay, so the sinusoidal y support the acceleration is equal to what? So y is equal to y sin omega t. Again, just to differentiate with respect to t, we are going to get y omega cos omega t. Again, double differentiate with respect to, we are going to get minus omega square y of sin omega t. Okay, so these are the three, just to differentiate, you are going to get this again from the equation number 1. Substitute y double dot value on that equation. Okay, so if you substitute in that equation, you are going to get what? M omega square y sin omega t. Okay, so this m omega square y is nothing but y f naught. Okay, so just to substitute f naught is equal to sin omega t, so give equation number 2. This equation is called as relative motion of the equation. Okay, remember this f naught sin omega t is equal to mz double dot plus ez dot plus kz is equal to what? Relative motion. Okay, so where f is equal to m omega square y. Okay, let us assume that the steady state relative amplitude is z, and it is lacks the acceleration by an angle phi. Hence the steady state solution is z is equal to capital Z of sin omega t minus phi. Okay, so this is phi is called as phase angle. Okay, where z is equal to, we already derived this. Okay, so z is equal to what? M omega square y square root of k minus m omega square whole square plus c omega square. Okay, so in the phase that is z by y is equal to, just to take the y this side, so y z by y is equal to omega by omega n whole square whole divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Okay, so here z by y is called as a relative displacement of transmissibility. Okay, so this is about the two, and the phase angle is what? The tan inverse of 2 zeta omega by omega n square root whole divided by 1 minus omega by omega n whole square. Okay, so this is about the phase angle and the relative equation. Two equations are there, so you have to remember. Okay, so I hope you understand these two derivations, I hope. Okay, so in the next class we are going to, so again here some one step will be there. Okay, so here you are not, I am wrote directly here, and here z is equal to m omega square y whole divided by square root of k minus m omega square whole square plus c omega square. Okay, here I wrote the direct equation, so z by, here one more step is there. Okay, I am going to tell you. Okay, so here z by y is equal to square root of omega by omega 1 whole square. So this is about the relative displacement, but here instead one more step is there. So here just to rearrange this equation, omega square and m omega square. Okay, so you are going to get this equation. Okay, so similarly in the previous case only. Okay, I hope you understand this. Okay, thank you very much.